and next time we will be starting to speak about duality theory, and I think that's probably chapter 6 in your text. Okay, so remember initialization once again. This is where the initial dictionary happens to be infeasible, and then you want to come to a feasible dictionary, and then you can run the same optimization phase as we did before. Now, last time we looked at this example, and the feasible region for that example, we see that 0, 0 is not part of that feasible region. And when we look at the initial dictionary, we see that some of the basic variables are negative there, right? And so we get an infeasible dictionary. But we see that the problem itself is feasible, right? The problem itself has a non-empty feasible region. So the question is then, how can we come up with a feasible dictionary? And then we introduced this idea of auxiliary problem. So the auxiliary problem was we look at when we add a auxiliary variable to the right hand side of the inequalities, or you can say, if you look at the right hand, you're adding the auxiliary variable x0 to the right hand side of the slack form. And doing that, once you do that, then you get this auxiliary problem, where in the auxiliary problem we are minimizing x0, which is we are maximizing negative x0, and then we have the same constraints, except that we are adding the auxiliary variable x0 on the right hand side. And then we're going to set up the initial dictionary for the auxiliary problem. And let's see, where is the initial? Here is the initial dictionary of the auxiliary problem. Okay, in the auxiliary problem, what's the objective? Objective is maximizing negative x0. Now remember what we said. One thing you need to remember is the auxiliary problem is always feasible. Okay, there is always a feasible solution of the auxiliary problem, whether or not the original problem has feasible solutions. It doesn't matter. Auxiliary problem will always have a feasible solution. Second, when you apply pivoting operations to the dictionary for the auxiliary problem, when you look at the optimal value, so the auxiliary problem will have an optimal value. Okay. Why? How do I know the auxiliary problem will always have an optimal value? Because we said that the auxiliary problem is always feasible, and it is unbounded. It is not unbounded, right? Which means it's bounded. Okay. So we know that there is an optimal solution for the auxiliary problem. And now, if the optimal value, so now remember the optimal value for the auxiliary problem, and that's the minimum value of x0, right? And if the optimal value for the auxiliary problem is 0, then you know that the original problem is feasible, and the final dictionary of the auxiliary problem will give you a feasible dictionary for the original problem. If the optimal value for the auxiliary problem is not 0, then what? Anyone remembers? If the optimal value of the auxiliary problem is not 0, then what can you say about the original problem? It is infeasible. The original problem will be infeasible. We're going to see an example today of that. So okay, so what's the pivot now? What's the initial? Initially, remember, once we set up the first dictionary for the auxiliary problem, the first dictionary will be infeasible. We do a trick here, which is we are going to force x0 to be the entering variable, and then we pick the basic variable with the least value to be the leaving variable. So remember, our x0 will be entering, and then which one is leaving? Well, you can either x3 or x5, any one of them could leave, because both of them have value. The value of x3 is -2 and x5 is also -2. So I can pick any one of them as the leaving. I'm trying to pick the basic variable with the least value to be the leaving variable, and in that dictionary the value of x3 is -3, the value of x5 is -2. Sorry, both of them are -2. So x3 leaves, and then we get our first feasible dictionary. Once we have our first feasible dictionary, then the pivoting operations are exactly the same as before. Okay? And however, there is only one thing, which is whenever possible, make x0 to be the leaving variable. Okay? After the first pivoting, x0 becomes basic. So whenever you get a chance, kick it out from the basis. Okay? Because once x0 becomes non-basic again, you know that you got the final dictionary. Why? Because if x0 becomes non-basic, then the value of x0, which is the objective function, will become 0, and we know that that's the minimum possible value of x0, because x0 is non-negative. Right? So we did that, and we came to a dictionary here where in this dictionary x0 became non-basic. X0 became non-basic, and then we know that we got the final dictionary for the auxiliary problem. So what's the optimal value for the auxiliary problem? The optimal value for the auxiliary problem is 0. x0 is 0. Remember, you were trying to minimize x0 or maximize negative x0, and we see that x0 is 0, so that's the minimum value. Because x0 in the optimal solution is 0 for the auxiliary problem, we know that the original problem is feasible now, so we can write down the feasible dictionary for the original problem. And how did you do that? Well, you delete the column for x0 altogether, delete the column for x0, keep all the other columns, and you have to change z. Okay? So this z here, that's the objective function for the auxiliary problem. But the z function for the original problem is different. Remember, the z value for the original problem was this x1 plus 2x2, right? And now, again, you get a feasible dictionary for the original problem by deleting the column for the auxiliary variable and keeping all the other columns, and then you have to change z. Original problem z was x1 plus 2x2. So what you're going to do there is that in the dictionary, x1 and x2 are basic, right? So from x1 and x2 row, I can read off the values of x1 and x2 in terms of the non-basic. So what is x1 in the dictionary? x1 is given by the first row, right? This is 2 plus 2/3 x3 plus 1/3 x5. And then what is x2? x2 is oh, you know what? I wrote x2 first. If you don't mind, let me just say, let me just do the following, okay? We have x1 plus 2x2. So this would be 2 times that, so that's x2, and x1 is 2 minus 1/3 x3 minus 2/3 x5. Okay, so from there you can read off what z should be in this dictionary in terms of the non-basic variables. So what am I getting? What should be the constant here? Am I getting 6? Am I getting 6? You can verify that? Okay, what would be the coefficient of x3? What would be the coefficient of x3? Anyone? Yeah. Coefficient of x should be 1. What's the coefficient of x5? What's the coefficient of x5? 0. Is everybody okay with that? Okay. So once I have that, let me just delete that. Okay, so that's now the initial dictionary feasible, right? Feasible initial dictionary for the original problem. And now we can do the usual operations and optimize the original problem now. Okay? Is everybody okay with that? Okay. And I'm not going to show you that. We have done many examples like that. So now let's do a different example. So this is a new example. I didn't give you that in the handout, I think, last time. Okay, so the question here is maximize the objective function z, which is x1 plus 2x2 minus x3, subject to the constraints x1 minus x2 less than 5, x2 plus x3 less than 14, minus x1 plus x3 less than negative 6, minus x3 less than or equal to negative 7, x1, x2, x3, they are all non-negative. Okay? This is the original problem. Now, this example, this problem that I had is actually infeasible. So what do I mean when I say this problem is infeasible? What is the meaning of saying that this problem is infeasible? Very good. You cannot satisfy all the constraints. That is, some of the constraints are contradictory. Okay? That is, there is no solution. There is no feasible solution. There is at any point in space. This is a three-dimensional problem. There is no point in space which is going to satisfy all the constraints. And so let's see how. Let's see how I know it is not going to be feasible. We can only do this because we have only 2-3 variables. We can do it by hand. Why this is not? Why this is infeasible? But imagine in real life, most of the problems have a lot of variables. You wouldn't be able to eyeball infeasibility of the problem. So I'm going to show you how we use the auxiliary problem to show that this is infeasible. Now, why is it infeasible? Let's see. Let me use red, maybe black. Let's look at the first two. Let me call this constraint C1, C2, C3, C4. Okay, and let me first of all say, if I add C1 and let's add C1 and C2. What do we get? If I add C1 and C2, what do we get? So what is C1 plus C2? What do I get? If you add C1 and C2, what am I getting? X1 plus X3 less than or equal to 19. Okay. Now, let's look at C3. C3 is, so now add it to C3. Add it to C3, yeah. What do I get then? So this is C1 plus C2. Now I'm adding C3 to it. What am I going to get? You know what? Let me just say add C1 plus C2 plus C3. Okay, that's probably the best thing to say here. Okay, let me, because I'm yeah. So that's all I'm doing really. So let's add C1 plus C2 plus C3. What am I getting? 2x3 less than or equal to 13, right? You agree? All of you agree with that? So what does it tell me about x3? Less than or equal to 13 divided by 2. Now, so this is what I get if I am adding the first three constraints, right? Now, what is a C4? What is C4 telling me? C4 tells me that x3 is what? x3 is greater than or equal to 7. Now what is 13 divided by 2? What is 13 divided by 2? 6.5, right? 6.5. So I get x3 less than 6.5, and I'm getting x3 bigger than 7 at the same time, right? So these two are contradicting, right? Am I making sense? So this implies, so this here together with this implies infeasibility of this problem. Is everybody okay with that? You guys agree with that? Now, of course, like I said, we could only detect something like this for a small problem by hand, but for bigger problems, well, you want simplex to tell you that it's infeasible, right? When you get an answer from the Excel, right? If you give Excel an infeasible problem, it better tell you that you got an infeasible problem. Otherwise, you would be. It's no good, right? So this is. So let's see how we can get this infeasibility answer from initialization phase. So this problem, to begin with, you see that some of the numbers on the right hand side are negative. So if I look at, let's look at the slack form for this problem. So this is the slack form. This is the slack form of the problem. Okay, so all I did is I added slack variables x4, x5, x6, x7, and all the variables are required to be non-negative. Okay, so that's the slack form. Once I have the slack form, from the slack form I'm going to be solving for the slack variables, and if I do that, I am going to get the initial dictionary, and the initial dictionary will be infeasible, right? The initial dictionary is this one. So once my initial dictionary is infeasible, then what is my trick? My trick is to turn to the auxiliary problem. And so we're going to set up the auxiliary problem. How do I set up the auxiliary problem? Well, the objective function for the auxiliary problem would be that you will be maximizing negative x0, and then you are going to be adding a auxiliary variable where? I mean, I'm looking at the slack form now. The slack form, you're going to be adding the auxiliary variable on the right or left? On the right hand side. So this is the auxiliary problem is maximize negative x0, same as the slack form, except that you added the auxiliary variable on the right hand side. Okay. So once I have that, I can write down the initial dictionary for the auxiliary problem by solving for the slack variables. So I do that. So solve for the slack variables, and you are going to get the initial. If you are writing it down, if you want me to stop somewhere, let me know. Initial dictionary of the auxiliary problem will be like this. Okay. which is the same initial dictionary for the original problem, except that you have x0. Okay. Now the objective row would be 0 minus x0. The objective row would be 0 minus x0, right? Because the objective function is what? Minus x0. Okay, so I have the initial dictionary, which is infeasible, right? This dictionary is at this moment infeasible because I have some negative numbers there. Now, what is the first? What is my entering variable at this stage? Can someone tell me what's the entering variable? What's the entering variable? And what's the leaving variable? What's the entering variable and what's the leaving variable? Yeah, x0. Remember the first, for the auxiliary problem, always the first pivoting operation, x0 is forced to be the entering variable. And then the leaving variable will be the one with the least value. So if you look at x4, x5, x6, the value of x4 is 5, x5 is 14, x6 is negative 6, x7 is negative 7. So x7 would be the leaving. X7 would be the leaving variable with the with the largest negative number there, right? The basis variable associated with the largest negative constant on the right hand side. Now, well, once I do choose them, then how do I go to the next dictionary? What do we do? X0 will enter, X7 will leave, right? So what's the pivoting operation now? X7 leaves, so look at the row for the leaving variable. From there, I can solve for x0, right? I can solve for x0, and whatever I get for x0, I'm going to put that for x0 here, right? In the objective row, I'm going to replace x0 by whatever value for x0 I get from the row for x7. Now, once I have done that, then I have to also replace each x0 on the right hand side by that. Am I making sense? So solve for x0 from the fourth row and then substitute that for x0 everywhere, right? Substitute that for x0 everywhere. And if you do that, you are going to end up with this second dictionary, and the second dictionary will be feasible, right? The second dictionary will be feasible. Now we do our usual operations, right? Once I get a feasible dictionary, this is the second dictionary, and this is feasible. Let me call that D2, and the previous one, let's call that D1. Okay, so now what's the leaving and what's the entering variable? So someone tell me now, what should be the entering variable and what should be the leaving variable? Anyone in the back? What's the entering variable and what's the leaving variable? How do you choose entering variable? I'm sorry? Yeah, so x3 will be the one because the coefficient of x3 is the largest. This is a maximizing problem, right? So the entering variable would be x3. Okay, once I have x3, then I have to detect what is the leaving variable. Let me delete this because I need that space. Let me say that here, D2 and this is feasible. Now, how do I detect the leaving? Okay, so what the entering variable x3. So keep the column of x3, keep the constant column, and delete everything else. So assume that nothing else is there. Now ask yourself from the first row, how large can you pick x3 without making x4 negative? What's the largest value of x3 you can pick without making x4 negative? 12. Okay, to go to the second row, what's the largest value of x3 you can pick without making x5 negative? I'm sorry? 21 divided by 2, right? 21 divided by 2. In the third row, what's the largest value of x3 you can pick? Half. What's the largest value of x3 you can pick in the last one? Okay, which one is the smallest? So my leaving variable would be x6. So my entering is x3, leaving is x6. Everybody is okay? Okay, so now I am going to write down dictionary number. What would be this would be D3, right? Okay, now I have this. Now what is the entering and what is the leaving? What is the entering variable here? Anyone in the back? What's the entering variable? What is the entering variable? Well, I mean, once again, you look at the non-basic variables and pick out the one with the largest coefficient, and in this case, obviously what? x1 has the largest coefficient. And then what would be the leaving? Well, again, we have to delete all the columns except for the constant and the column for x1. So look at, let me highlight them. I'm looking at the constant column. The constant column and the column for x1. Now we are asking ourselves, from the first row, how large can you pick x1 without making x3 negative? How large can you pick x1? As big as you want, right? Because it's plus half x1. Now from the second row, how large can you pick x1 without making x4 negative? It will be 23 half over 3 half, right? So what is that? 23 over 3. You agree with that? Now, from the third row, how large can I pick x1? 20, right? And in the last row, I can pick it what? 13 half over half, which is what? 13? Which one is the smallest? What is 23 divided by 3? Yeah, so that's the smallest, right? So I see that x4 would have to be the leaving, right? Everybody's okay? So once I detect the leaving, then what? From the row of the leaving variable, solve for the entering variable, and then replace each occurrence of the entering variable by that, okay? By its value. And if you do that, you get your new dictionary. So now we are getting D3. D4. We're going to get our D4. Okay, so that's D4. Once again, what's the entering? Well, all the coefficients are negative except for one of them, so that's pretty easy to detect. Okay, once again, what's the leaving? Once again, I have to highlight. Whoops, what's happening? Let me highlight. Funny. Okay, so now look at the column for x2 and the constant column. From the first row, how large can I pick x2? How large can I pick x2? As big as I want, right? Because I have positive 1/3 x2, so no matter how big x2 I pick, x3 will remain positive, right? So anything you want. How big can I pick x2 in the second row without making x1 negative? Without making x1 negative, I can pick x2 to be anything again. When I say infinity, I mean I can pick it as big as I want. And then in the third row, I see that I have 37/3, and the coefficient of x2 is a negative 5/3. So when you have a negative coefficient there, you know that there is a bound for x2. So divide 37/3 by 5/3 here. If I do that, what do I get? 37/5, which is about 7, right? And then in the last row, 8/3/1/3. So what is that? 8. Which one is small? Which one is small? 37/5, right? Because that's 7 something. So you get this is the leaving. Okay, so that was D4, and then you write down the next dictionary, D5. In D5, okay, so I write down D5. Now, if you look at D5, what do you see? Is it the final dictionary? Yeah, because I don't have any more. All the coefficients of the non-basics are negative, so there is no candidate for entering variable, right? So I'm done. This is the final. This is the final. Remember what we said, the auxiliary is always feasible and bounded, so it has a optimal solution. And what's the optimal solution? What's the optimal solution? So remember, we were trying to what? Maximize negative x0, right? So the objective here, z was negative x0, right? Right? And what's that value? What's the optimal value? Negative 1/5. So what does it tell you about the value of x0? 1/5. Do I have to prove this is not 0? Right? And well, if it is not 0, then what do we know? If it is not 0, what do we know? What's that? This dictionary is feasible, but what do we know? The original is not feasible, right? Since the optimal value of x0 is not 0, the original problem is infeasible. Is everybody okay with that? So that really ends the discussion of initialization. Any questions? Anything about initialization? Anything about initialization? So let me end by some final remarks here. The pivoting operation number 1. The pivoting operation number 1 is what? It's always you force x0 to enter, and then which variable leaves? Which variable leaves? The basic variable with least value leaves. So this is the strange pivoting operation, which is not the same as what we did before. Once we have done that, we have done that, this next dictionary is always going to be feasible. Next dictionary is feasible. Okay? Now pivoting operation is as usual. When I say as usual, I mean the same as for the optimization phase. So it means that the entering variable would be the variable with the largest coefficient in the objective row, and then once you have that, look at the column for the entering and the constant column, and figure out as you increase the entering variable, which of the basic variables goes to 0 first. Okay? Which of the basic variables goes to 0 first? That's going to be determined by the ratios that we look at, and then you pick out your leaving variable. Once you have the leaving, then what do you do? Once you have the, can someone phrase that? Once you have the leaving variable, what is it that you need to do?
Entering variable column, constant 0, and then figure out which row has the lowest value of the entering variable that doesn't make the entire equation or that it doesn't make the...
I think you're talking about how to pick the leaving variable, right? Is that what you're saying? What I'm saying is once you pick the leaving variable, then what do you do? Once you pick the leaving variable, then you're going to rewrite the dictionary, right? Right? And then what do you do to rewrite? What's that? Okay, so
isolate the entering variable.
Now I'm talking about any of the dictionaries. So, given any dictionary, you pick an entering variable. I'm not talking about x0. Pick an entering variable. Pick a leaving variable. Then what do you do? I'm asking you to phrase that.
So the equation for the leaving variable.
Look at the equation for the leaving variable. Yes.
Isolate the entering variable.
Yes.
And then
to solve for that.
Yeah, and then substitute in that new equation.
Yeah, very good. So solve for the entering from the equation of the leaving variable, and then substitute that for every occurrence of the entering variable everywhere, and you're going to get the new dictionary. Okay? Or remember how there was another way we phrased it, which was you are going to use the elementary or row operations just like you do on matrices, and try to make you have to get the coefficient of entering variable 1, right, and all the other coefficients of the entering variable 0 everywhere else, and if once you do that, you automatically obtain the new dictionary. Okay, so now the last step is, so you're going to do that, and then so we are talking about the auxiliary problem, and as you go through the dictionary, so let's say you have D1, D2, and then ... At some point you come to your final dictionary for the auxiliary problem. Okay, so let me say this is the DAUX star. So this is by that I mean this is the final dictionary for the auxiliary problem. So this is the initialization. And once you have that, you look at the objective value, corresponding objective value. So let me just say Z aux star, that's the objective value for the auxiliary optimal value for the auxiliary problem. Now, what are you going to conclude based on that? Z auxiliary star, that's the optimal value for the auxiliary problem. And how are you going to make your decision based on that? There are two possibilities, right? One, it is not 0. If it is not 0, then what? Then I conclude the original problem is feasible or infeasible? Infeasible. If it is 0, then I can say the original problem is feasible, right? And can obtain a feasible dictionary for the original problem from the final dictionary DAUX star, right? And let me just say that I don't want to try to write down in phrases how you do that, but the idea is that you delete in the final dictionary, X0 will always be the non-basic. You delete the column for non-basic, you get the dictionary for the original problem, except that the objective row needs to be changed, right? How do you change the objective row? Go back to the original objective function. You say this is, let's say this is x1 plus x2 plus x3. You replace them by their values from the dictionary. You read off the values of them, of the decision variables for the original problem from the dictionary, and then rewrite Z, right? Any questions? All right, so then I assume that we are done.